In the previous videos, I told you if you have, in general, if you have a rigid body with bunch of forces on it, and maybe moments, then we have these equations about for this rigid body, for the dynamics of this rigid body. Sum of the forces is equal to mass times acceleration of the centroid of that rigid body. And also we have sum of the moments about the centroid is equal to Ig times alpha. We cannot take the moment about any other points and use this equation. So these are general equations, they are always true. But sometimes we have some specific case. Sometimes our rigid body is rotating about only one point, let's say point O. And the centroid of it is in a different point, like for example, G. So it is rotating about point O, so we are gonna have angular velocity and angular acceleration. In this specific case, we can use this equation too. We can use sum of the moments about the centroid is equal to I about the centroid times alpha of it. But when we are using this equation, you need to consider the forces that we have, the reaction forces that we have at O, and find the moment of them about point G as well, right? Because we need to take the moment of all the forces that we have about point G. Let's say we have a bunch of forces here, maybe moments. Then when we are using this equation, I need to have this M, calculate the moment of F1, calculate the moment of F2 about G, and also calculate the moment of OX and OY about G to use this equation. But we have a simpler equation to get rid of these two forces too. We can prove, the proof is quite easy. We can take a look at the book. I'm not gonna do it here. We can take the moment about point O as well. Sum of the moments about point O is gonna be equal to I about O times alpha. So if I want to use this equation, I can use it for a rigid body which is rotating about a point like O. If I want to use this equation, then the moment of these two reaction forces about point O is going to disappear because they are not making any moment. So I don't need to worry about these two reaction forces. But the difference between these two is in this one, we are taking, using Ig, mass moment of inertia about G, but in this one, we must use mass moment of inertia about point O. I'm gonna use this to solve a bunch of equations, a bunch of problems later and show them in different videos for you. But before doing that, let me complete this with another one. If I have a rigid body, again with some forces on it, maybe moments, and for some reason, I don't want to take the moment about G. I want to take a moment about another arbitrary point like point P, for example. But the point P is not pinned to the ground like the previous case. Can I take the moment about point P? Yes, there is an equation for that specific case. If you want to take the moment about P, arbitrary point P, then sum of the moments about point P is going to be equal to I around the centroid times alpha plus rho cross MA what is this rho? Rho is the vector which goes from point P to the centroid. This is point G, the centroid. So for any reason, if you want to take the moment about any other point, that's not going to be equal to Ig times alpha. And that's not going to be I about P times alpha. we have to use this a little bit more complicated equation. Sum of the moments about this point P is going to be IG times alpha plus rho vector from P to G times mass times acceleration of the centroid. So we should know this equation. And also, I'm going to show you another useful equation which is less complicated than all of this. And in that equation, in that method actually, we can turn a dynamic problem to a static problem. What is that method? That method is this. Again, let's say we have a rigid body with some force and moments on it. And this rigid body is moving at this moment, for example, in this direction with acceleration of A. And also it is rotating with angular acceleration of alpha. So we have a rigid body, acceleration of the centroid of it is ag, and acceleration of the rotational acceleration of it is alpha. Now, this is the trick. By this trick, you can turn this dynamic problem to a static problem and deal it with like any other static problem. Which you can say sum of the forces in any direction is equal to 0, sum of the moments at any point is equal to 0. What is that trick? We need to add a force, an imaginary force, to the centroid with the magnitude of m times acceleration of the centroid, but in the opposite direction. So if the acceleration is in that direction, then I'm going to add this imaginary force to this rigid body. Mass times acceleration of the centroid. Actually, to make it more accurate, negative m times acceleration in this acceleration of the centroid. And also, we need to add an imaginary moment or torque opposite to the direction of alpha. And the magnitude of that is going to be IG times alpha, actually negative alpha. And this is a moment. Moment is a free vector. You can put it anywhere you want. It doesn't have to be at this point. If you do this, then your problem is going to be a static problem after this point. Then considering this moments among all the other moments and also this force among all the other forces, then you can say sum of the forces in any direction is equal to 0. And sum of the moments about any point is equal to 0. You don't have to take the moment at the centroid. It's like a static problem, right? In the static, you can say sum of the moments about any point is equal to 0. We have the same here too. But when we are doing this, you need to consider this force as well among all the other forces, and also we need to consider this moment as well among all the other moments, moment of the forces or given moments.